So let's do the introductions. Would you like to go ahead, Sophie, and introduce yourself? And I'm going to introduce myself after that, and then we can begin.
So I'm Sophie Marquez from the University of Stellenbosch. I am a mathematics lecturer there with Prof. Zurab.
I am also from University of Stellenbosch. My name is Zurab Janelidze. You can call me Zurab. I also like the kind of mathematics that you saw yesterday with Cyrene and Sophie, and we will be doing a bit more of that. We are going to build on what we did yesterday and continue to some interesting places from there. Eventually, we might arrive to the same destination where you arrived yesterday, but maybe through a little bit different route. So let me begin by taking us back to sets. I have a set of notes for that, which I'm going to share with you on the chat. So I'm sharing a link on the chat. You can open that on your side if you'd like to. Otherwise, I'm going to show it on the screen as well. And then at some point, I'll switch to Blackboard.
Someone cannot hear. Is there anyone else who is in the same situation? Maybe it's on your side. Okay.
So these are some notes that I made in January the 3rd, as you see here, a while back. It introduces the idea of a set. For those who might not have been here yesterday, let's do a little recap of what a set is. I like the following example that I chose for these notes. You see a photo of apples, right? There is one photo and there are many apples. Now we can think of these many apples as one thing, thanks to the fact that all of them fit in one photo. And that's basically what a set is, when we think of many things as one thing. Then we call these things elements of the set. So if now we're looking at the set of apples, the elements of that set are the individual apples. Then we have some way of writing sets down, which you already saw yesterday. But if you haven't, here's a little, I'm going to revise that a little bit. Firstly, it's useful to have a way of writing down the apples themselves. We don't want to draw the apples all the time, and if we draw the apples, it might look similar, and then we might not be able to tell which one is which. So one typical way of using symbols for representing objects is, for instance, to use a letter combined with a number. Usually the number would appear as a subscript of your letter. On this post, I didn't have feature of writing subscripts, so I just wrote the number next to the letter, like A1 and A2 and so on. So let A1, A2, and up to A8 represent these apples. And it doesn't matter in which order. We could think of this apple, for instance, the one that you see to the bottom left corner, to be A1 and so on. But then when we want to think of these 8 apples as one thing, in other words, as a set, we put these curly brackets around the list of the apples. So, Sophie, are you able to see when I highlight?
Yes, I can see it.
Wonderful, thanks. So this would be the set of these apples, and the curly brackets here mark the fact that it's a set. And then there is an exploration, and already yesterday I asked some of you to perhaps try out this exploration, and maybe you have, and if you have, you might want to share with us what results you got. Let me first formulate this for everyone, those who haven't seen it before. So you see here a few sets, right? Here's the first set, here's the second set, here's the third one, and the fourth one. Now the question is, which of these four sets is the same set as the one that we've got here? So that is the question we want to explore. I'm now going to switch to the blackboard, write out all these sets, and then we can engage in a discussion which of these four are the same set as this one. And also we'll, of course, talk about why that is so. Why in mathematics is very important. Basically, all of mathematics is about understanding why something is so or so. Let me see, where is my blackboard? Here it is. So the initial set we were given is the one whose elements are listed as A1, A2, A3, A4, A5, A6, A7, and A8. And then we are given four other sets, which might not all be different from this one. And we want to determine the differences. So one of them is the one that consists of A1, A3, A2, A4, A5, A6, A7, and A8. The second one is the set consisting of A1, A2, A3, A4, A5, A6, and A7. And as I'm writing these out, you can start thinking and comparing these sets with the first one that's given here to determine which of them is the same as the first one, which isn't the same. Then we have A1, A2, A3, A4, A6, A7, and A8. And finally, we have A1, A2, A3, A4, A4, second time, A5, A6, A7, and A8. Now, in order to refer to these four sets easily, we're going to represent each of them as well using a letter. So let's call the first one, let's call B. The second one, let's call C, D, and E. And now I would like to open this for discussion. There is already an answer in the chat. So a few of you are telling me that it's the set B that's the same as the first one. Maybe we should have a name for the first one as well. Maybe we don't need that. Let me write it rather this way. So I'm going to write our hypothesis now, and then we'll see if we all agree with that or not. So the suggestion is that this set equals to B, or rather B equals to the other set. Okay. Let's see. Could you explain why do you think that these two sets are equal? They do look different to me. Sophie, do they look different to you?
I guess I would need to understand what do you mean by equality in order to know how.
Well, that's the whole point of this exploration, to figure out what should be equality of sets based on the intuition that we might have developed from yesterday's session. So let's first try to explain this hypothesis we made here, that this must be equal to B, and then we can discuss whether maybe other sets are also equal or not equal to that set. The difference I see between these two sets is that in the first one and the top one, the A2 and the A3 appear in the order I said, but in the second one, the order is reversed. So does the order not matter? Those of you who said that it's B that's equal to the first one, would you like to tell us if you think that whether the order in which we list elements in a set matters or not? Thanks to Melo, so you're saying that the order does not matter, but Nako is saying that it does matter. The notion of a set, as it was introduced yesterday, was a form of abstraction, right? We talked about abstraction. What we're going to be doing today is to talk about what I call concretization. Concretization can be seen as a process where we take something that's abstract and we try to turn it into something that's concrete, but it will be concrete in a different way than the initial entities that it was abstracting. So in this specific case, we want to have a more concrete idea exactly what is a set. The thing is that when we talk about equality of objects, right? We can tell whether two things are equal when we have a very good concrete sense of what these objects are. So in a way, being able to determine whether two things are equal or not corresponds to having a concrete understanding of that concept. There are a few more answers in the chat. Some of them say order does not matter. Some of them say order does matter. Order matters in a different concept, the concept of a sequence. In the concept of a set, order does not matter. And this is just by the design of the concept of a set. So if we go back to this set of apples here on the picture, let me share that picture with you again, or rather maybe I'll copy the picture here. So we have this photo with apples. You can see here that it will be very hard to determine the order in which these apples appear on the photo, or either it will be impossible to determine, or there will be many ways of figuring out the order, right? And we did say that this photo is supposed to represent a set of apples. So if it's hard to determine order on the photo, then maybe the order should not matter. Otherwise, when we said that the photo represents a set, we were not quite accurate, right? So I would like to propose that the order in which we list elements of a set does not matter. And thank you very much for Tumela to remind everyone that yesterday it was discussed that pattern or sequence is not the same thing as a set. And that's a very good remark. Now that we know that the order does not matter, we can indeed claim that the set B is equal to the initial set. But what about the other ones? What about C, D, and E? Are they, some of them, still perhaps equal to B? So let's look at C. If you think that C is different from B, which we now know is the same as the first set, would you like to point out why? Why is C different from B? I agree that C is a subset of B. So let's use the notation from the previous session. C is a subset of B. I agree with that because every element that goes inside C also appears in B. So then by the definition given yesterday, C must be a subset of B. But perhaps it's equal to B. And if you think it is not, why not? I see, Peter, thanks for that. You say it's because of A8. A8 is contained in B, but it is not contained in C, right? we cannot find A8 here. So B has one more element than C. So while C is a subset of B, B is not a subset of C. And when subset means that every element in the first set must be inside the second set, we do want the two sets to be subsets of each other if we are saying that they must equal each other. We can, in fact, even use this as a definition of equality of sets. So let's write this out. Two sets B and C are equal to each other if and only if B is a subset of C and C is a subset of B. I'm going to underline if and only if here. As you probably already know, if and only if means it's a two-directional implication, right? So if B and C are indeed equal to each other, then B must be a subset of C and C must be a subset of B. And also the other way around. If it happens so that B and C are subsets of each other, then they must equal to each other. Maybe it will be convenient also if I introduce a symbolic notation for equality of sets, which is standard, which makes use of the standard equality notation in mathematics. I should have rather maybe put this one here. Facts like these, facts that describe very, very fundamental nature of things we're looking at, facts that concretize our abstract concepts, and that can be themselves impossible to break down into more basic facts because they're really the starting point of mathematics. They're called axioms. So this will be our first axiom about sets, which talks about the nature of equality of sets. Now that we have this axiom, we are more equipped to continue on with our investigation. But before we continue, are there any questions so far? Was everything clear up to this point? I'm sorry to... Yes, please.
Can I add something to relink with what we said yesterday about when we were trying to abstract some property, and then we want to describe a set of objects through those property. For instance, set would be a property. And once you have identified what you would like to concentrate on the object, knowing when two of those object with this property is equal is fundamental part of mathematics and give you a good understanding, as Zorab say, of that object. So at some point, as soon as you define something, you should have a subsequent definition which tells you when these two of this something, or at least a remark, are equal or are the same as object.
Yes, I completely agree with that, Sophie. And in my thinking, that I attribute this as one of the aspects of concretization, because in that process, this abstract concept obtains a more concrete shape in our mind.
Yeah, exactly.
But what about others? So could you maybe give me some feedback whether you're fine so far, whether everything was clear so far, and we can move on, or if not, then you can ask some questions. I'm sorry to hear about the connection problem, Lebogang.
I think there is a question from...
What is concretization? Well, we could have a separate 2-hour discussion about this word. In today's session, I'm using this word as a way of making the abstract concepts more concrete, almost that we can feel them as we can feel objects in real life. Yesterday, I was watching the chat, and a few of you said that it was too abstract, even though you enjoyed it a lot. A few of you said that it was too abstract and so on. And indeed, that happens in mathematics. When you first start abstracting, you don't get the sense that things are so abstract that it's difficult to have a grasp on those abstract ideas. That's when we use concretization to turn them into something that's easier to grasp and something that is almost like concrete existence in our mind, even if it is not really a real life object. In terms of what I said about axiom, the term axiom is used to represent a mathematical fact that is a very basic fact that helps us concretize the abstract idea, and also that is difficult to decompose it further into even more basic facts. So it's almost like a starting point for doing mathematics with the abstract concepts that we've introduced. But you will get handle of these notions, of these terms, as we go along with having more examples of concretization and an axiom. Let me suggest now we go back to the specific exploration we were conducting here, and I hope that all of you understands why B is indeed equal to the set we were given in the beginning, and why C is not equal to it. And now let's investigate D. Is D equal to that initial set or not? What do you think? And if you think it's not, then explain why. If you think it is, then explain why as well. So we've got a very good question from Paulos. But before moving to his question or her question, sorry, it's his question, I guess. Let's first look at D. Is D equal to B? Thank you very much, Nako. The reason why D isn't equal to B is because D is missing something. It's missing A5. C was also missing something. C was missing A8 and D is missing A5. So because of that, D is not equal to B. So just like C, D is a subset of B, but as in the other case, B is not a subset of D. Very good, Tumelo. Thanks a lot for your input. And now let's come back to the question from Paulos about E. What is interesting about E is that we have a repetition of elements. You can notice that everything seems to match with the elements of the initial set, except that A4 is written out twice. Now, does that count as two separate elements? Because if it does, then it will have more elements than B, then therefore E and B cannot equal each other. Or does this repetition gets ignored, and does it count as one element, in which case E and B will equal each other? What are your thoughts about this based on the abstraction that you've performed so far in terms of grasping the concept of a set? What does your intuition suggest to you? Should repetitions count as forming different sets, or should they be ignored, and then this would make E equal to B? So Tendo suggests that maybe they should count as two separate elements. Are there other thoughts about this? let me make the following comparison. Imagine I want to describe to you the set of apples. Okay, there's a very good comment from Nako who says that B is a subset of E, but E is not a subset of B. Let's look at E and B carefully. Is it true that E is not a subset of B? What does it mean for E to be a subset of B? Doesn't it mean that every element of E must be an element of B? Now we start picking the elements from E and comparing them to elements of B. So A1 is an element of E. It happens to be in B as well. A2 is an element of B. So it's in B. So the same for A3, right? A4 is in E, but also it's in B. The same applies to the other A4, because as far as B is concerned, these two A4s are the same A4. So even though most of you are saying that E is not a subset of B, I would like to suggest that perhaps it is, because every time I will pick an element, you see, every time I pick an element from here, let's separate it out from the rest, I will be able to find it there. I can match it with one of the elements there, right? Even if I pick out the A4, you see, I will be able to match it there. And the same applies for the other A4. I can still match this there. That's one way of thinking, and hence employing our axiom to determine that maybe actually E is equal to B. And the other way is that what we're really doing here with this notation is that we are naming the apples we see on the picture, right? So let's name them: A1, A2, A3, A4, A5, A6, A7, A8. Now, if there was another apple, would we have given that other apple the same name, A4? Exactly, you're right, Zamodita. So the picture does not have two A4s. It only has one A4. But now imagine that we now insert another apple on the picture, and we call that one A4 as well to match the set E. Would this be a good way of representing the apples symbolically? Because isn't there a problem that now we're going to be using the same symbol, A4, for representing two different apples? Will such a representation be an accurate representation? Exactly. Thanks, Lasetti. We would say A9 instead of A4 for that other apple. Thank you very much, Pixala. So the way we might still end up mentioning A4 twice is, for instance, in a situation where I'm telling you what these elements are, A1, A2, I'm not describing the set to you, I'm telling you, we've got A1 there, we've got A2 there, we've got A3 there, we've got A4 there. Then my phone rings, I pick up the phone, I start talking about over the phone, and then I stop the phone conversation, and I forgot where I stopped. And I would not sure what I said last, and I continue. And then we've got A4, and then we've got A5. So I accidentally repeated A4 twice just because I forgot I already mentioned to you. So that's one way we could have a scenario where A4 would be mentioned twice, but in fact, it represents the same apple. So it does mean that A4 will be counted as one.
Zurab?
Yes.
Could you perhaps concretize what inclusion means?
Subset inclusion.
Yes.
Yes, I will do that. But before I do that, I still want to make one final remark in the previous explanation, namely that once again, if this was a sequence, if it wasn't a set, but a sequence, a pattern, then these two terms would be regarded as two different terms. Indeed, we could consider the sequence 1, 1, 2, 2, 3, 3, 4, 4, and so on. This is not the same sequence as 1, 2, 3, 4, and so on. As a sequence, they're not the same thing. But in a set, just like the order does not matter, which does matter in a sequence, in a set also repetitions will not matter. And now let me go back to the request from you, Sophie, to concretize what does it mean that one set is a subset of the other, so that we can determine that indeed E is a subset of B, and knowing that also B is a subset of E, we will then be able to say, okay, by our axiom then, E and B must be the same set. So let's write out the definition for being a subset in more concrete form. A set E is a subset of a set B if and only if every it depends now which approach I take here. If I say every element of E is an element of B, then this only helps us partially, because if I go back here, I pick this element out, this A4 and then the other A4, then there is still this question of whether they are the same element or not, and whether the second A4 is actually a different A4 to the first one. And should it be different, then this different A4 will not match with that A4 in B, which perhaps matches with this one. But the whole point of concretizing symbolically, that we assign this symbolic representation to objects, is that we can tell that the two things are the same as soon as they have the same symbolic representation. So because it's the same symbol we use, A4, here and there, they must be representing the same object. So that takes us back to that explanation we had before, where in a diagram like this, we wouldn't want to use the same A4 for two different apples. Sophie, did I do what you asked me to do?
Yes, you did. So if I understand well, if you list all the elements of the set, and you choose symbol to determine the elements, then those symbols, if they are the same, they should represent the same element.
Yeah.
And if they are different, they should be different element.
Not the second one. Sometimes we can have two different symbols representing the same object still. Here's an example. 2 squared and 2 plus 2. Symbolically, they look different from each other, but they represent the same number, that number being 4.
I see.
Before I know, so I could have introduced letters for these before I figured out that, before I computed and figured out that actually both of them are equal to 4, I might have been using different letters for them. And then it turns out that they're the same. So two different symbols can represent the same thing, but the same symbol cannot represent two different things.
So the key is that everything needs to be very clearly stated before you set your set.
Exactly. And that's the whole idea of concretization. When things are concrete, they are clear. So we want to concretize abstract ideas so that they become as clear to us as the real life objects around us. And in fact, for a mathematician, these abstract ideas are indeed not very different. I mean, for me, number 2 is not less real than the computer I'm using now to talk to you, to all of you.
Okay. So you, if we wanted to be more precise or more concrete. We should have said, given A1, A2, A3, A4, A5, A6, A7, A8 distinct elements, we construct this.
Yeah, exactly. And in our case, that was somehow assumed because we said that these these symbols represent the actual apples on the picture. So we didn't make it explicit, but it was implicit that they would have ended up being different objects. But you're right. If we didn't have apples as a starting point, and if we just had a list like this, then we should have made it clear, made it precise whether it's possible or not that some of these A's are actually the same object, which theoretically is possible, but in our case it was not possible because they represented the different apples on the photo. Great. So that is our first part of the exploration 1.1 in my notes. So we go back to those notes. And then there is also a second part, which we're going to attempt to do.
And I just, there is a question from Nako on the chat and a question and a comment from Tumelo. Maybe you might to address them.
Okay, I didn't see question marks. I thought they were just comments.
Nako a little bit earlier.
Oh, sorry. So the number of elements in a set E does not matter as long as it consists of every element set B has. Well, that's a good question, Jakob. The thing is that when we count elements in a set, we count according to which of them are distinct from each other. So we wouldn't say that we wouldn't say that E has 9 elements, even though in the list they appear to be 9 of them because A4 has been repeated twice. We would still say that E has 8 elements because repetition doesn't matter. However, once again, if I think of this as a sequence, if I remove these curly brackets and maybe I put round brackets or maybe nothing, and I really think of this as a sequence, the way that you learn about sequences at school, then there are 9 terms in this sequence, because a term is defined not just by the actual object, but also the location. And there are 9 locations here. 1, 2, 3, 4, 5, 6, 7, 8, 9. So this sequence has 9 terms, but the set only has 8 elements. And to know that it has 8 elements, not only we need to know that these A4 will have to be the same because they're the same symbol, but also what Dr. Marcus pointed out to us, we would have to know that all the other A's are all different from each other, which we did in this example because they represented different apples on the photo. So that's how we know for sure that E will have 8 elements. So if I have an abstract set like something like F equals set consisting of X, Y, Z, without knowing what X, Y, Z are, I will not know whether it has 3 elements or not. It could be that it has just 1 element. It could be that all X, Y, Z, all 3 of them represent the same number 5, for example. So if all of them are equal to 5, then the set ends up having 1 element, not 3. And that's again, so this notation requires, symbolic notation sometimes requires further concretization in order to be able to count, let's say, elements in a set.
I see that Pozzo has an end. I don't know if you want to speak.
Yes, please go ahead, Pozzo, if you're able to. Oh, you are not able to. Let me give you permission to do that. Allow to talk. Feel free to unmute your microphone. You're going to say something. I've just copy-pasted the second part of exploration 1.1 from the notes. Let's see what it says. And maybe I want to combine that with the picture we had. So let me copy the picture over here as well. Just like we could add apples to a photo or take some away, we can add elements to a set or take them away. Well, here would be an example. See if I start with a set of just A1, A2, A3. I could take one of the elements away and be left with a set consisting of just A1 and A2. You could physically pick an apple from that set of 8 apples and then take another picture, and then the new photo will only have 7 apples in it, right?
I think some might have trouble to read, and they are suggesting to put it in bold or bigger, I guess.
We'll do that. I'll make it bigger and thicker as well. Is that too big? Let's see. That's a bit too big. Is this better? Oh, now it's yellow. I hope that's fine. Peter says that he's not seeing the screen at all. I'm very sorry to hear that, Peter. I don't know what could be the cause of that. You can only see our faces, not the screen. Maybe you can open the that's a good suggestion to quit the webinar, come back, but it should be a way to have a list of all the videos and also the screen, and then you can point to the screen and say, click on the smaller version of the screen and say spotlight for me, or spotlight for, or add pin or something like that. So, example of taking things away, we could start with a set consisting of A2, A1, and A3, and we can take away A3 from it, and then we get the set having just A1 and A2. Now we can take away A1 and A2 as well, right? And if we take everything away, eventually we will end up with this thing that we discussed, that you discussed yesterday, which is the empty set. There's a good suggestion from Raquel. It could have been better if everyone just put on their video and Prof could teach like that, because everyone is going to complain. Not Sophie, did you understand that comment? So it will be lovely to see everyone, of course, on the screen, but how will that help with seeing the shared screen? I'm not sure. Ah, wonderful. Peter sees the screen now. That's fantastic. So the question now is, this empty set that we get after taking all the apples away from the photo. Okay, sorry, that's not the question. The question comes after. Apologies. This is just an explanation of the empty set, which is something you already saw yesterday. And here is the next exploration. Start with a set of 3 apples and a set of 3 mountains. So let's begin with a set of 3 apples and a set of 3 mountains. 1, 2, and 3. And let's represent the apples by A1, A2, and A3 as we did before, and the mountains by M1, M2, and M3. Now,
Zurab, Nako will have load shedding at 12. He's asking, we will share the video on
yeah,
YouTube.
the video will be shared on YouTube, and the participants will get the link
Okay.
to the video.
And the notes of Zurab are also, will you share them?
I'm saving these. I mean, these are very chaotic notes, but I am saving them, and I can also share them. But what I'm going to do, maybe it will be easiest for now. I can simply make a blog post on my blog with these notes, just for quick access before the YouTube is set up and so on. So this is my blog, and when you open it, you will see the latest post will contain exactly these notes. So we start with 3 apples and 3 mountains, and we take away 1 from each. So let's take the third one, then we'll get 2 apples and 2 mountains. Then we take away 1 more time, we get 1 apple and 1 mountain. Now in this process, you see each time we had different sets. So this set of 3 apples is of course different from the set of 3 mountains, because there's no way any of the apples can be the same as any of the mountains, right? They're different sets. Here too, they are different. And at this level too, they're different. But what happens when we take away the last remaining elements from each? So we take away this final apple from here, we will end up with the empty set. Will that still be different or not from the set of mountains where we have no mountains? So in other words, is the set of no apples different from the set of no mountains? What do you think? So in this exercise, we are concretizing the idea of the empty set. Lebegang says that he doesn't think it will be different. Would you like to explain why you don't think they will be different, Lebegang? So a very important thing in mathematics is that mathematics is not just about the answers, it's even more about the explanation that confirms the answer than it is about the answer itself. So every time we do something, we want to be able to explain what we did. That's a nice explanation to Mello. So if I may rephrase what you said, you're basically telling us that if these sets were to be different from each other, we should have had an element in one that we can't find in the other. And there is no such element because both sets have no elements in them. And it seems like Nako also agrees with you. Well, I agree with that too. And we can actually perhaps apply the axiom to confirm that conclusion as well. So let me remind you of this axiom about equality of sets. According to this axiom, 2 sets will be equal when they're subsets of each other, right? So now let's take the left-hand side empty set, the empty set of apples, let's call it B, and let's call the empty set of mountains C. And now we are trying to determine whether B is a subset of C and whether C is a subset of B, because if they're subsets of each other, then they will be equal according to this axiom. So now we're kind of giving some purpose to the axiom. We introduced the axiom as a way of concretizing what a set is, and now we can maybe, it could help us in concretizing our idea, why should these 2 empty sets be the same set? If we look at the definition of subset, right, when is one set a subset of the other? It means, according to the definition, that happens when, if I go back to the notes here, that happens when every element of one set is an element of the other set, right? So Is it true that every element of B is an element of C? Is that true? When there is nothing in B and there is nothing in C? And the explanation here could be that when we are saying every element in B is an element of B, well, yeah, that's great. Thanks for your answers to Mel and Raquel. So I agree with you, because when we're saying that every element of B is an element of C, what we really mean is that every time I can find something here, it must also be found there. And this is really true simply because we can find nothing there. So it's kind of true for the absence of any entities inside or any elements inside this set. This is actually a very deep question. It shouldn't be overlooked in our context. Now that we've already intuitively got convinced that these two sets should be equal, maybe it's easier to understand. But it's actually a very difficult concept. Why, in the case when B is empty, it is still true that every element of B is an element of C. And to show you how difficult it is, even the third-year students sometimes struggle to understand why this is so. But I'm not going to, since you all feel comfortable for now, I'm not going to go in depth there. As if I do, then it will take us to logic, mathematical logic, which will require its own 2 hours of introduction. So for now, let's just be content with the fact that we seem to agree on the fact that for the case when there is nothing in B, everything in B will automatically be in C. And maybe just to abstract this phenomenon a little bit, would we then be able to derive the fact that this empty set, so now that we know there is only one empty set, because if something has no elements in it, then any other thing having nothing in it will equal to it. Do you think you will then agree, by the same principle that made us believe that B was a subset of C, that the empty set will be a subset of, let's say, the set of 3 apples? Do you agree with this as well? So we could use the same explanation. If there is nothing in here and there are three things there, for the left side to be a subset of the right side, we have to check that every time I can find something in there, the same thing can be found in here. But that's true simply because there's nothing that we can find on the left side. Are we all happy with this, or would you like to talk about this a bit more? I'm sorry to hear about the internet problem, Paulus. All right, let's elaborate on this. So let's try to, okay, before we elaborate on this, let's go back here and let me first ask you, do we all agree that the empty set of apples will equal the empty set of mountains? If you don't agree with that, or you don't understand why the empty set of apples should equal the empty set of mountains, let us know. If you agree with that, then we're going to move on to and re-explain the other thing I was saying here. Okay, great. So at least we seem to agree on this one. Now let's move on to here. So we want to determine whether the empty set, which is a set having nothing in it, is a subset or not of this other set. The way we defined the subset relation, we said that in general, if I have 2 sets, X and Y, X being a subset of Y means that every element that can be found, I'm now expanding, concretizing my definition of subset to make it more clear how we can apply it in this case. Every element that can be found in X can also be found in Y. I'm not sure I follow your explanation, Tumela, about 0, 1, 2, 3, though. That I didn't follow that one. So in the case when X has no elements and when Y has 3 elements, why is it so that every element that can be found in X can also be found in Y? Well, you can think about it like this. Imagine one of you tells me it's not so. Sophie, can I maybe ask you to claim that X is not a subset of Y, that it's not true that every element in X can be found in Y?
I want to. I do understand why it might be why it is problematic, but let us say that I can find an element in X which is in Y. What will happen?
So if it is not true that every element that can be found in X is also in Y, it means that there should be something in X that we can find that we can't find in Y, right?
But that does not make sense because X does not have anything in it.
Exactly, yeah. Ah, that's a nice way of thinking, Nako. Now I understand what you meant. So Nako says we could reduce this principle to the previous principle as follows. This is a really nice explanation. I haven't ever thought of this before, and I'm certainly going to use your explanation in the future, Nako. I think your explanation is actually much better than mine. So Nako says, well, to determine that empty set is a subset of that thing, let's do the following. We know that empty set equals the empty set of A's, right? Because we determined before that every 2 empty sets are the same. Now the empty set of A's can be obtained from the empty set of A1 by removing A1 from it. And when we remove something from a set, we do get its subset. In turn, this one is obtained by removing something from that set. So this must be a subset of that. And the same way here. And so we have, this is a subset of that, it's a subset of that, it's a subset of that. So that would make this subset of that. That's a nice explanation. Is that what you meant, Nako? While you're responding to that, I want to, wonderful, yeah, thank you very much, Nako. This is really a nice way of thinking about it. So, because establishing that 2 empty sets are equal is more intuitive, and then using that to derive that empty set must be a subset of basically every other set, right? It didn't really matter what we would have here. The way that you derived it is really a nice approach. But let me go back to a comment here from Raquel, who says that 0 can be found in X. 0 cannot be found in X. To be able to find 0 in X means that 0 would be one of the elements listed inside X, but it isn't because X has nothing in it. So in notation, X being the empty set makes it different from a set which has something in it, namely 0. 0 could mean nothing. Okay, I could replace 0 with nothing. Here is the empty set. So these two things are still not the same thing. And let me elaborate on that one, because this is a very important point in concretizing the idea of a set. So there is a difference between, okay, let me actually go back to right from the beginning of this hour, when we said that we can think of many things as one thing. Like we can think of 3 apples as one entity, and that is the set of those 3 apples, right? So there is a process in our mind that allows us to think of many things as one thing. Now, what happens when we apply this process to nothing? So when we initially start off with nothing. So I'm just making my screen bigger. If I start off with nothing, and I think of that nothing as one thing, which will be my empty set, this thing is no longer nothing. It is now a thing. It is one thing, in fact. It has nothing in it. There are no elements in it. But this itself is no longer nothing. And this is actually a very important philosophical point as well, because we are kind of creating here something out of nothing. And to help you see what I mean here, think of a set as a single thought of those many things. You can certainly create in your mind a thought of nothing, can't you? So think of nothing right now. In your mind, you've got a thought of nothing. Fixate on that thought. Now I'm claiming that you're thinking about something because you've got one thought in your mind, as opposed to somebody else who at this moment might really be thinking of nothing. So there are no thoughts in their mind. So there is a difference between the empty set and the nothing. The empty set is the nothing seen as one thing. And once we understand that, and then we iterate this process, we do the second time. Now we take that one thing and think of it as its own one thing. We're going up the hierarchy here. We will end up with something like this, which is no longer the same as the original one, because this thing has something in it, whereas the other one has nothing in it. Yeah, I'm laughing, I'm smiling at your remark. So as soon as we represent nothing using a specific concrete symbol, let's say this symbol, right? That nothing now becomes something, and we should still distinguish between the nothing and the something it became after we represented it. And this reminds me, Sophia, of our theory of distinguishing. Maybe we should point them to our article on a very, very interesting magazine called Bizarku magazine, where you will find many interesting articles. Among them is an article that Sophia and I wrote about the principle of distinguishing being, in a sense, the most fundamental principle for understanding mathematics. And it already applies here, where you want to distinguish between this, which is nothing, and that seen as one thing, which is the empty set. In terms of your question, Raquel, about our next class after this one, we will have to ask this question to Dr. Ratilal. She is in charge of the abstract algebra classes. But we can also, if there is a request from you here, if you want to have more of these classes sooner, just let us know, and we can arrange that. Tando says, nothing can never really be nothing. Yeah, so once you thought of nothing, you already have something in your mind. You got a thought of nothing, so it's no longer nothing itself. I mean, it is nothing in the sense that it doesn't have any elements. As a set, it doesn't have any elements. But once again, as a set, it's one thing which could be an element of other things. The analogy with bags is interesting. Let's explore a little bit that analogy, Nako. I'm going to create a new file now because my previous Blackboard is full. So just give me a moment to do that. That's fantastic. I'm very glad to hear that, Raquel. Absolutely, we can organize more classes like this. The only thing is, of course, that you and others also have school, and so the question is how to do it in such a way that it doesn't interfere with your school schedule. So maybe you want to give us some suggestions as to which time of the day and which days would be most convenient for you if we did organize these sessions more often. Let's go back to the analogy of bags. So we were tasked to go to a shop and buy some apples in the shop. So we take a box with us, and we hope to put some apples in this box from the shop. And there's a shop there. So we walk to the shop, we enter the shop, and we find the table of apples there. And we put these apples in the box. And now we've bought 2 apples and we bring these apples home. Okay. As a result, at home, we're going to have a box with 2 apples. Now, there is a difference between a box of 2 apples and these 2 apples lying in the shop. What is the difference? The 2 apples in the shop are not inside a box. And at our place, we put them in a box. So this can be seen as a way of distinguishing between the collection of these apples before we thought of it as one, and the collection of apples after we think of it as one. So here we just have A1, A2. These are the 2 apples, and here we have the set consisting of A1 and A2. Now let's perform the same experiment, finding that in the shop they don't sell apples. They ran out of apples. So what will happen? We'll come back empty-handed, right? Not quite. We will still have the empty box in our hands. Whereas in the shop, there will be no apples. So when you come back home with no apples and your family greets you and they tell you, oh, you brought some apples for us. And you tell them, yeah, sure, there is. In the first case, they will be happy because you actually did bring 2 apples. In the second case, they will tell you, but you haven't brought you have brought nothing for us. There are no apples there. And you can answer, well, I did bring something. At least I brought the empty box. So the empty box of apples is something, right? And so that's how we might want to think of the empty set. And then using this analogy, as it was suggested by Nako, we could consider the empty box inside another box. So we've got empty set inside another set. In this sense, then, the two boxes are different. On the left side, it's a box with nothing in it. On the right side, we have a box with something in it. What is that thing in it? It's another box. So that's why we will not have the empty set being equal to that other set which has empty set in it. This analogy with boxes, however, can be very dangerous. And let me show you another example where, I mean, in this specific case, the analogy is nice because it helps us understand what do we mean by having a set whose element itself is empty set, and how is that different from the empty set. But there is another example that completely ruins the idea of a set. Imagine I put an apple inside this smaller box. So let me actually make a different picture with that. I'm going to come back to the discussion about the times for next session. So if I put an apple in this smaller box, then we will get a set. On the right-hand side, we will get a set.
Raquel is raising her hand. I don't know if she has a question.
Yes, please go ahead, Raquel, if you would like to ask something.
Professor, I just wanted to know, like as you said, with the empty box and the empty box inside of another empty box, the empty box that is inside the empty box, doesn't that make the box not empty anymore?
It does.
Because because there is something in that box which does not make the whole box empty.
You're absolutely right, and that's exactly why we said that this set is no longer empty. So that's why we said it's not equal to the empty set. So does that fit with your understanding, Raquel? Great.
Yes, it does. Great. Thank you.
But now I'm going to show you that the box analogy doesn't always work. And here is the example where it will not work. So let's consider the set B2. The B2 is the set that has one element in it, which is the set with apple inside. This apple, is it going to be element of B? Would one of you would like to answer what you think? Whether, so sorry, I meant to write B2 here. So B2 is a set which has one element in it, and that element being that set. So let's call this thing something. So let's call this set A. A is the set with the orange apple inside. Okay, that's very good, Nako and Tumelo. I think your intuition is absolutely correct there. So the orange apple is not. It's not an element of B2. even though the orange apple appears to be inside the bigger box, but it actually is inside another box that's inside that bigger box. It's not directly inside the bigger box. And so the reason why I said that the box analogy doesn't always work is that you might think that now this orange apple is inside the bigger box in terms of space that it occupies, right? It occupies some space inside the bigger box. So then maybe the orange apple should be an element of the bigger box, but in fact it isn't, according to how we want to think about sets. So the orange apple is an element of the set A. So the orange apple is element of A. A itself is element of B2, but that does not make the orange apple element of B2. This does not make that element of, because if it did, we would have then written down, so let me make B3. We would have had orange apple standing there on its own without any curly brackets around it, in addition to the other one. If the orange apple were to be an element of B3. This is how it would have looked like in set notation. The relationship between the apple and the bigger box goes via A. And this is now, might remind you of the discussion you had yesterday about relations of knowing each other going via a third person that was in between. So the relationship between the orange apple and the set B2 is that orange apple is element of something that's an element of B2. But orange apple directly is not an element of B2. Now, another way that the box analogy breaks is that this set, the one I've written here, that doesn't make sense in terms of boxes. Why not? Imagine that means that, so here by the apple, we mean the same apple. So these two orange apples are meant to be the same. So let's call them A3.
I think Zurab, someone is Tumalo is having struggling to understand.
Okay, so let me not, thank you. Let me not go further yet. So would you like to tell us, Tumalo, exactly where it stops making sense to you?
I'm feeling, as you had said, that the orange apple is not an element of B2. So I'm failing to understand, if the orange apple is not an element of B2, doesn't that make B2 an empty box?
It doesn't make B2 empty because B2 still has a different element, A. It has element A in it. So the element of B2 is the box containing the apple, but not the apple itself. The apple itself is element of A. Does that make more sense?
Yes, thank you, sir. I think I understand it now.
Raquel, did you want to say something? You had hand up and the microphone on. I muted you, sorry, because my voice was echoing, but if you want to say something, please go ahead. I wanted to show you another situation where the box analogy is really disastrous for understanding sets. So consider this B3. Now, according to how it's written out here, B3 contains A3 in it as an element. So inside this box, we can find the apple. But at the same time, it contains another element, another box, in which we should be able to find the same, exactly same orange apple, because remember the same symbol represents the same entity, which it will be impossible, right? You cannot have an apple inside that box being outside the smaller box at the same time being inside the smaller box simultaneously. That cannot work. So sets are not the same as boxes. And this is part of concretizing the idea of a set, because the abstraction that we performed yesterday and also the beginning of today about sets, it still was a vague concept. It could have meant many other things as well. But now, as we're talking more about it, when we're giving more concrete meaning, we're seeing exactly what it is. That's the whole point of concretization, to have a more concrete grasp of this abstract concept, so that every time we are given something, we are exactly sure what the elements of that set are and how that thing is a set, and so on. Once you have a concrete grasp of an abstract concept, you can work with that abstract concept as if it was a real object you're holding in your hand. You not only are able to do precise thinking about it, you even have feelings supporting your thinking. So you will feel the properties of that abstract entity once you obtain a concrete understanding of it. And it is possible to reach that kind of understanding. That's all what mathematics is all about. And the amazing ways mathematics applies to real life in technology, for example, right? Which is, I guess, the main example, is thanks to this concretization. Mathematicians are able to compute things in a very abstract world, the world of abstract ideas, and yet they apply them and it works according to their computations. And how is that possible? Because if it was abstract, how can we come to such concrete conclusions in this abstract realm that they actually work in real life? And the secret to that is that even though it's abstract, it's still possible to concretize that abstractness. And in our minds, it becomes almost as concrete as real life objects, so that by working with them mathematically, we are able to make an effect on real life, which corresponds to our mathematical predictions. Those of you who have raised hands, please go ahead, unmute your microphone. You can ask your questions.
So I understand from what you said previously that a same symbol represents a single, what you said in the beginning, when we had the A4. So now, I want to understand, if you have the same object appearing twice, like you did with the box example, that we still consider it as one object, even though it's the same object appearing twice.
We still consider it as one object. And this is exactly why the boxtionality doesn't work. Because in a box, we couldn't have had that same object in two different locations. Does that make sense?
So like, I'm trying to say, if it's like, let me make an example with like twins. Let's say there was, I'm just gonna make the example with twins. So there's one identical twin in the box where there's the one apple, and then there's another twin with another apple, but they're not the same people, but it's the same. I don't know if I'm making sense.
You're making perfect sense. Because they're different people, we would not use the same symbolic representation for them. We would then call one of them A3 and the other A4. Even though they look the same, they are different people, so we will use different symbols for them.
Can I, for me,
Please,
for the box, the way I think about it is, I think about the box as a sealed box, where you put your apple and you seal it with paper, and then you cannot kind of see what is inside if you are not able to pick element inside your box. So in a sense, you will have another box, but the element inside your box that you can pick are only the box themselves, not the apple, which are like inside the box.
That's a nice way of thinking about it. Yeah, that's a nice way of thinking about that. That solves this problem. That definitely solves this problem, but I don't think it solves this problem. Where A3 is now at the same time inside this smaller sealed box and outside of it.
Yes, because you will have two elements. Like yesterday we said, but we don't have to have the same type of element. So one element will be the sealed box and the other element will be.
Exactly, but A3 being element of the sealed box at the same time as being element of the bigger box, that cannot work in real life. We won't be able to package.
Okay, yeah.
In such a way that,
yeah.
One way we can make it work is at one point, so we can also think of this as something that happens through time. That today we're going to put this apple right here, tomorrow we're going to put it there, and then we say that the elements are those things that occurred at one of the days, and we put all of them together. So that could work then, but it's a bit going kind of taking the intuition off track. So if the sets are not boxes, and you might have been now developing this feeling, and now you're understanding sets better, but now this breaking analogy, so Bismarck is asking, basically B3 doesn't exist. It exists mathematically. It doesn't exist as a box. So you can think of the box analogy as boxes being special kinds of sets. You can have sets which are not modeled by boxes, and here is a way of thinking about it. Take this apple, take a picture of it, take a photo of it. Okay, now you've got the photo, print the photo and put it next to the original apple. And take a photo of that. So the photo analogy is much better than the box analogy for this specific purpose, right? So you can still say that, okay, maybe this apple is no longer the same as that one because this is now the picture of the apple, no longer the original one. And then my explanation breaks, of course. But if we don't distinguish between the actual apple and the one on the photo, then this could explain how we could have a set of this kind where we have A3 and then another element which inside has A3. And of course, taking a photo is something that happens through time, right? First we took the photo and then we placed the photo next to the original apple. So it's similar to this time involvement in the analogy that we discussed, that I mentioned earlier.
That's what I thought, but it's the same idea as having time.
Now, this brings us to a very interesting concept, the concept of time. In a sense, the reason why mathematics is abstract compared to real life is because mathematics is able to model things that instead of these things existing statically in one moment in time, they exist over time. Time itself, for example, will you say that time is concrete? You can't smell time, you can't taste time, you can't touch time, you can't see time, you can't hear time. So in a sense, time is almost as abstract as mathematics, right? It doesn't, you cannot experience time in one moment, right? So in a way, mathematics is a toolbox for understanding and picturing and working with things that exist across time instead of existing in one single moment of time. And this time element, the time component of mathematics is embodied already in the concept of a set. In this way, what we discussed here. So you could think of this as it's not that this apple and the same apple simultaneously are inside and outside the box. It's just that this set describes a process where one day the apple was inside, the other day it was outside. Which makes sets very powerful in expressing things that happen in time. And one of the first things we would want to express that's very important to time is the concept of a function. Functions model things, they model processes that happen in time. And we will see how we can actually encode functions as sets. But for that, we will need the concept of a relation, which we ended on yesterday. And I was hoping that today we're going to do a bit more of that, but we are approaching the end of our time. So might not be a good idea to start with a new topic. I might still want to maybe show you a little bit of what would have been next if I had more time in this session. Perhaps you would like to explore this on your own. This would be the lesson 2 in my blog. So let's have a look at that. It's just a synopsis of what's in lesson 2. We're not going to go in depth right now. Just to give a little introduction for you to possibly look at yourself. I should warn you, the concept discussed here in this lesson, the concept of quotient of a set, is a very, very advanced concept. Third-year students in mathematics often struggle with grasping this concept. And Sophie knows much more about this than I, because for the last few years you've been dedicating some of your courses to teaching this concept, right, Sophie?
Yes, that is true. And it's
Yeah.
not only a third year, it's also even fourth year.
I see. I see. So it is an advanced concept, yet it is possible to start getting some abstract idea about this concept already now. And this is what lesson 2 aims. And hopefully in our sessions, we will be able to concretize this concept more and more. The general idea is quite simple, really. You've got, let's say, your set of books. So here is the set of books. But as you see, these books are arranged on shelves. So you kind of categorize or classify your collection, your elements in the set. You can arrange your elements in a set according to color, according to shape. If they're books, you can also arrange them on shelves. So this general idea of arranging things by grouping things together inside a set and forming several groups, like in this case, the groups will be the actual books in the shelves. That's the abstract idea behind the concept of a quotient of a set. But of course, the concept of quotient of a set will be a concretization of this abstract idea, and that concretization is the difficult part. Question from Nako: is the kind of math done at university by first years? Well, no. Somehow, many times we find that the curriculum we have, even at university, isn't quite caught up with recent development that it's in mathematics. For instance, number theory existed since a long time ago. Mathematical study of sets is much more recent, and it hasn't been quite integrated into school mathematics, or even first or sometimes even second year mathematics at university. There was actually an attempt once to teach school mathematics based predominantly on sets. It was a failed attempt. Many say that it was failed because the teachers were not prepared for the material. Some say it was failed because the parents were not able to help their children. I think probably the reason why it failed is because sets, from the first look, seem very easy things. It's really easy to say you've got a collection of things, but as we saw today, when you start concretizing this, it's quite an advanced concept, and probably that's why they fail, because the concept is quite advanced. But in the third year, we do expect students to have some understanding of set theory. even if it's not taught explicitly, the language of set theory is used for various things in the first and second year. So by the third year, we expect students to have a good grasp of this language. At Stellenbosch University, we do teach some of set theory explicitly in the second year already, but it's not true for every university. Yeah, thanks to Mola for your remark. Indeed, maths is a lot of fun and interesting, and the pedagogical approach and the route one takes to get into maths very much influences the experience. It's a bit like a tour guide, right? Imagine we are on a tour, and I could be a tour guide that takes you through very, very difficult paths, and you have to jump from one cliff to another and so on. That would be a horrible experience. On the other hand, I could take you on an easy route. The good solution is, of course, a balance of the two. Experiencing challenges and learning how to overcome them is very important, but one should control that the challenges do not outweigh the enjoyment that one gets out of these challenges. So it's a very, very delicate balance in terms of how one enters into the world of mathematics. But yeah, the purpose of these lessons is to show you the beautiful side of mathematics, even though it can be challenging and difficult. We have a lot of time here to explore these challenges. We are not tied by exams or marks, which often are the reason for stress. So we can explore this purely based on our enjoyment. Sophie, do you have a suggestion? What do we do next?
It's up to you. Maybe we could give them an opportunity of giving feedback, or what do you think?
No, that's a good idea. Perhaps before we do that, let me answer the question of Bismarck. Is set theory part of real analysis? Real analysis is a subject that got quite advanced before set theory became a mathematical subject. So it's possible to do real analysis with minimal exposure to sets, but nowadays set theory did become a very integral part of the language of mathematics. So no matter what approach you take to study real analysis, you will end up working with sets. This will most of the times be sets of numbers, but you will need to use the intuition behind sets to understand topics for real analysis. So set theory is not part of real analysis, but real analysis does rely on a good understanding of set theory. The second question is, will these classes continue? The answer is yes. They will definitely continue, especially if there is an interest from you. Third question is, how can I improve in maths? Well, Sophie, shall we try to answer this together?
My first point would be, what are you struggling with the most in math? Because you need to identify what your problem or where your understanding is not right, or whether your way of working through math might be changed in order to get more understanding. Can you identify what do you struggle the most with math?
That's a very to the spot suggestion. I wouldn't have been able to think of anything better, but even this that you said, Sophie, it feels so obvious, but I didn't think of that at all. But now that you said it, it reminds me that actually this is one can abstract this principle. So when you want to solve a mathematical problem, you want to first understand what the problem is. And you do want to spend quite a lot of time reflecting and trying to understand the problem itself before attempting to solve it. And that principle also applies to the problem of how to improve in maths. Did I make a fair abstraction of your idea, Sophie?
Yes, because I feel that often your problem can be resolved if you reflect back on thinking, pinpointing. If you already manage to say, oh, I'm struggling right now in math because of this reason and this reason, you are better off than you have no idea of why you are struggling in math. So you need to identify your problem. Can you identify your problem?
Would you like to concretize exactly how and where you're struggling in math, Chicos Fatso? While you're typing that up, there is an interesting question here. Can one view set theory as a mixture of applied mathematics and pure mathematics? I think this distinction between applied mathematics and pure mathematics is a bit of an illusion. So, is there a difference between West and East? Consider Earth. Earth is round. If you go this way, you're going west. If you go this way, you're going east. But there is no spot on Earth that's called west. Unlike north and south, there is no spot on Earth that's called west, and there is no spot on Earth that's called east. It's just the direction you're taking, right? Eventually, if you fully take this direction, you will eventually go around Earth, right? That's how I like to think about pure and applied mathematics. That applied mathematics is not kind of part of mathematics or a spot in mathematics. It's rather about the direction you're taking in your mathematical investigation. When you do applied mathematics, your goal, your direction is to solve a real life problem. You will be happy when some real life problem gets solved eventually. When you do pure mathematics, your goal is to understand mathematics more than what you understood before, or maybe to make a new mathematical discovery. Your goal is not specifically application. But now, the reason why these two goals are indeed circular is that when you develop new mathematics by just going after understanding, it very often ends up so that this new mathematics actually is very applicable. And so then taking the applied route will allow you to really make use of that in real life. And the other way around, when you're trying to solve real life problem, you might have to develop some mathematics to help you solve the problem. And this way you would have discovered some new interesting mathematics that might help you understand previous mathematics better. So applied and pure mathematics are really directions rather than actual positions inside the world of mathematics. And in that sense, set theory is indeed, you can go in the applied direction when you do set theory, and you can also go in the pure direction when you do set theory. For example, this year I'm involved in a project where we're trying to apply some ideas of set theory in music, which is very different from mathematics in the sense that music is considered as art and mathematics is science. But most of the time I spend my time going in the direction of pure mathematics. But yeah, set theory is useful for both directions, definitely. Would you like to add anything to that, Sophie?
No, I think you answered well. I'm trying to get, I think we might have several persons who are maybe finding a struggle with mathematics. I want to mention that struggling there is some research which say that struggle is part of learning, but there is two types of struggle. There is some unproductive struggle and some productive struggle. And to understand in which type of struggle you are in is quite a not easy task. To see if you are lost in an unproductive struggle where you cannot get your head out. So that's why I ask if you could tell me, when you see a problem, do you know how to start? Or are you already lost from the start? Because that would make a difference if you really don't know what to do from the beginning, or if you do know what you do and then you get stuck in the middle. But I don't know if they want to speak about it. Maybe they are a bit shy. But Bismarck has a comment for you.
Yeah, so struggling with problem-solving algebra questions, I think what I would add to what Sophie said is that try to identify the concepts that underlie your problem and concretize them in your mind. Do you have a concrete understanding of those concepts? Very often, by just reflecting on even the definitions of concepts involved in an algebra question, you will discover that actually your understanding of that concept wasn't as concrete as the problem requires. So the approach of concretizing might be a good approach there. Also, the approach of abstraction could be useful. You might be solving a specific problem, and by means of abstraction, you might notice that this specific problem can actually be solved in general ways by disregarding some concrete details which are really irrelevant to the method of solution. And so when you discard those details, then you see the abstract picture better. Then you can apply the mathematics methodologies you learned before. So by isolating the abstract picture, it helps you detect better which material you learned before is compatible with this material, so you can apply that methodology to solve the problem. But I personally wouldn't mind at all to have a session or two, or maybe even more, where we could pick some problems that you're struggling with, and we could talk about the methodology of approaching such problems. How do you, in concrete terms, how do you apply concretization and abstraction to find your way through solving a problem? That could be an interesting discussion. Another question, do you perhaps think that high school mathematics prepares first-year students for a mathematical curriculum in university? Let's put it this way. High school mathematics gives you some toolbox. But the question is, do you know how to use those tools? And that very much depends on how you approached high school mathematics when you were studying mathematics on your own. Very often, the exams and the marks do not reflect your true mastery of those tools. You can even get a high mark. It doesn't necessarily always mean that you actually have a concrete grasp of these tools. So when you come to high school, when you come to university, then that's when you might realize, actually, wait a second, so I'm lacking some tools here. Maybe I didn't understand math at school at the level I should have. So it's really a joint work of school and yourself. And it is possible to engage with school mathematics deeply enough that you'll be very well prepared for university. But it's also very easily possible to not do that, still get good marks and be very unprepared for university. So it really very much depends on your personal attitude to mathematics. Do you think you would agree on that, Sophie, or do you want to have an alternative perspective on this?
I think I do agree, but I think one of the principal problem, I would say, that we require or run from an algorithmic approach, which means that you want steps to help you, and instead you should prioritize understanding and question much more what is given to you. And if you are lucky and you don't manage to get through all your question, to find someone, maybe a study buddy, that will help you through questioning, like maybe if you speak together, even if you are in the same level, you would be able to already understand much more by communicating with each other. That's my feeling. So instead of being alone on your corner, I'm sure you can find some friends that are in the same situation of you, and they will understand things that you would not understand. And by asking each other questions, you will test your understanding of things. I don't know if that makes sense, Surab.
Yeah, it makes very good sense. I think we often underestimate how much we can learn from each other. In fact, to be completely honest, I think it is impossible to learn mathematics from books alone. Every single mathematician had someone, every single extremely successful mathematician included, every single mathematician had someone at some point in their lives that opened the doors, the key, the lock to the world of mathematics. Some people had more support than others, but this little support is always needed. Because of the abstract nature of mathematics and the so what the book fails to do is to take you through the cycle of abstraction and concretization, which is very important. And in human interaction, this cycle can be more explicit. But even if you're interacting with someone who is not a mathematician, you can still benefit from that, as Sophie is saying. I completely agree with that, because very often when we try to explain things to somebody else, I mean, look, what is explanation? Explanation is just a form of concretization. So when you have to explain something to someone else, already there you're engaging in concretization, and that can help you a lot. But of course, in addition to that, the other person's perspective could be very useful. They could see something that you might not have seen. No human being has universal intelligence. We each have a small portion of intelligence, and by interacting with each other, we help to build bigger forms of intelligence. And this is apparent in every aspect of life. I mean, everything we do that's really effective involves lots and lots of people working hard to the same goal. Yeah, absolutely. Mathematics is like a big community. Yeah, sorry, Sophie, I want to interrupt you.
No, I often, when my student comes and then ask me a question, in the end, I'd end up not answering the question, because as Zurab said, you see that process happening is as you concretize your question and your problem, you find the solution. So I think we should be a bit more social people than individualistic people. And I can tell you that even if you are the one who is always explaining to the others, you are in a very good space, because every time you explain, your understanding becomes stronger, and you are just making yourself better and better. So by being kind of people and explaining them, you are just making yourself become a better person every time, by many ways, human way and mathematically. So create yourself friends, not only friends to speak about random things which sometimes don't lead to something constructive. You can do those things, but also to speak about your coursework, speak about mathematics, and make it part of your day-to-day life. You have seen with this lesson of algebra how you could link mathematics with your day-to-day life. Maybe make it more like that, because it will, if it's more something that will be useful for you in an everyday basis, you will be willing to understand it better and have more deep knowledge about it.
Absolutely. Thank you very much to everyone. It was really, I think both Sophie and I, we are really grateful to you for giving us the opportunity at the end of this session to talk about, in more general terms, about the approach to mathematics. I think that was a very useful input to our sessions. And in terms of when will be the next session, this will be communicated to you through Dr. Sirin Ratilal. I can you're most welcome also to email me if you would like to, in case you don't receive some communication and so on. This is my email address. But we'll definitely keep in touch with you, and we'll continue working through abstract algebra. Bye, everyone.
Bye, and thank you.